In this video, we're going to do a brief review of the logarithmic functions. So we begin by defining what a logarithmic function is. So when we talk about log functions, we often refer to their base as well. So we say the log function with base a. These bases have restrictions on them, so they need to be positive and not equal to 1. So just like the bases for the exponential functions. So we would define the logarithmic function of base a as, let's say, a function f of x, and we would write log base a of x. Okay. Now, and if you want, you can have brackets around here, so it's log of x, and you have to have the thing inside the log be positive. Okay, so it's only defined for positive values of x. And the way we actually use it is we say that y is equal to log base a of x. This is equivalent to saying a to the power y equals x. Okay, so this is a very important relationship. And we're going to be using it frequently. So another way to say that is to say that log base a of x is the exponent we need to raise a to in order to get x. Okay, so the y here is the log base a of x, and that's the exponent up here. So a to the y is equal to the power x. Now the way that I always remember this relationship, okay, the base is the base, and the other things switch sides. So here the y is on the opposite side of the equals from the base, and on the other side it's with the base, and then the x that's in the log is now outside in the exponential version. Okay. I want to make a note, maybe I'll do it up here. So sometimes we would write just log of x, and when we do that, what we actually mean is log base 10 of x. That x isn't very good. Okay, so if you don't see a base, then you should assume base 10. And then sometimes also we write ln, okay, so ln of x. This actually stands for the natural logarithm. Okay, so you might hear the natural log, and what we mean by that is log base e of x. Remember, e is that Euler's constant, that special base for the exponentials. Okay, now these are actually the only ones that your calculator has in it. So these are the only ones that you can actually compute using your calculator. So all the others, you're going to need some sort of log rule, or you're going to need this relationship here to compute. Okay, so let's see some of those. So log base 3 of 9. So I want to say, okay, 3 to what power equals 9? Okay, well, I know that this is 3 squared equals 9. So that means that this log is equal to 2. Okay, so the base is 3. And we know 3 squared equals to 9. Okay, now for the next one, our base is 2. So we want 2 to what power, okay, equals 1 over 64. Okay, this is a tougher one, so we might want to write 1 over 64 differently. So this is actually 64 to the minus 1. And 64 is actually a power of 2. It's 2 to the power 6. So this is 2 to the 6 to the minus 1. So it's going to be 2 to the minus 6. Okay, so then our exponent that we need is actually minus 6. So this log is equal to minus 6. Okay, log base e. So this is actually ln of 1, if you want to write using the other notation. So we'd want to know e to what power equals 1. Okay, well actually, anything to the power 0 equals 1, so including e. So if you ever want a log of 1, okay, it's always 0. So that's just computing some basic ones using the relationship. So it's easier generally to work with the exponential functions and try to go back to the log functions. So you can probably see that the log functions are very closely related to the exponential functions. So let's draw them on the same grid here. So we already drew 2 to the x, so I'm just going to reproduce it for you. 4, 3 is 4, 5, 6, 7, 8. Okay, so it looks, oops, it looks like this. Okay, so this is f of x is 2 to the x. Okay, now what we're going to do is I'm going to do on this side, so we're going to take x values and we want to find their y values when y is log base 2 of x. Okay, now it's going to be easiest if I pick x values that are powers of 2. Okay, so 1, this is 2 to the 0, so the y value is going to be 0 here. Maybe I should write for a couple of them anyway. So this is log base 2 of 1. That's going to be 0. The exponent I need to raise 2 in order to get 1. Okay, so that gives me a point at 1, 0. Okay, now if I take the number 2, this is 2 to the power 1. So log base 2 of 2, the power I need to, this is going to be a lot of 2's here. The power I need to raise 2 in order to get 2, okay, is 1. Okay, so maybe I'll just, so this number is this power. Okay, this number is that power. That's why we're getting these. Okay, so now I'm going to have a point at 2, 1. Okay, I don't want to pick 3 because that one's actually hard. So, but let's try 4 because I know 4 is 2 squared. Okay, so then log base 2 of 4, this is going to be 2. Okay, I can also do 8 because that's 2 cubed, so that one's going to be 3. 4, and 4, 5, 6, 7, 8, and 3. Okay, so I get something so far that looks like that. Okay, this is 8, 3, 4, 2, 2, 1, and 1, 0. Okay, what if I did 1/2? So if I'm less than 1, this is actually 2 to the minus 1. So the log is going to be minus 1. Because remember, we're looking for the exponent of 2 in order to get the number. Okay, so that means at 1/2, I'm actually at minus 1. Okay, I can also do 1/4. Okay, this is 2 to the minus 2. So that's going to be minus 2. So I get even further. The closer I get to 0, the smaller my exponent's going to be. And remember that the domain is actually bigger than, I needed x to be bigger than 0. Okay, so what we get is actually a vertical asymptote here. Okay, now I'm going to write some of these points here. So for the 2 to the x graph, we had the point 0, 1, the point 1, 2, the point 2, 4, and the point 3, 8. Okay, now we also had the point negative 1, 1/2, okay, etc. What do you notice about all of these points? So the blue points and the purple points, they're just flipped over. Right? So all I did was switch the coordinates. Okay, that's not a coincidence. These graphs are actually a reflection of each other in the line y equals x. Let me just get a different color here. So if we draw the line y equals x, okay, it looks like that. The blue graph, if you flipped over that line, it's going to land right on top of the purple graph. So that's what happens when we have inverse functions. Okay, so it turns out that the log base 2 of x is the inverse of 2 to the x. So some facts about this relationship. Okay, so the domain of the log base a of x, okay, is the interval from 0 to infinity, and that's actually equal to the range of the a to the x graph. Okay, now the range of the log graph is negative infinity to infinity, so it grows. It's not approaching any asymptote here. It continues to grow, even though it looks like it levels off. It just grows very slowly. So it does get to infinity eventually. This is equal to the domain of the a to the x graph. Okay, also the point xy on the graph of a to the x means that the point yx is on the graph log base a to the a of x. Okay, so this happens when they are inverse functions. Okay, so what that means is if I take log base a of my a to the x, I just get x. Okay, and similarly, if I have a to the log base a of x, I also just get x. Okay, so the log and the exponential sort of cancel each other out. So they're very closely related. And also, so we know that the exponential functions have all these exponent rules that they use. Well, because of their close relationship, the log functions have a bunch of log rules that they use. So I'm going to give you some of them here. So these are some properties for logs. So if x and y are real numbers, positive real numbers, okay, r is a real number, and a is a positive number other than 1, okay, so it's an allowable, okay, this is allowable base, okay. Then we can say something about each of these, okay, so log base a of a, this is just a 1, okay, so why is that? So remember, we want a to what power, because that's our base. Okay, so our base. We want to know a to what power equals the other side, the x value, so that's a. So this is a to the 1, so our power has to be 1. Okay, so similarly, if I want a to what power equals 1, then I need that power to be 0. Okay, so if you want to take the log of the number 1, no matter what the base is, you're going to get 0. Okay, now this one also is very similar. So a, the base, to what power equals a to the r. Well, this is already a power of a, so then I have to have the same base. So this is going to be r. So essentially, the log and the exponential just cancel out, and I just get the exponent. Okay, some more interesting rules. So if I have the log base a of two things that are multiplied together, so x times y, what I can do is I can take log base a of x and log base a of y separately, and then add them. Okay. If I have a division inside, then again, I can do log base a of the top and log base a of the bottom and subtract the bottom one. Okay, I'm just going to do a little proof here so that you understand how these are coming from the exponent rules. So maybe let's do 4. Okay, so proof of 4. So let's let m be log base a of x and n be log base a of y. Okay, so what that means is that a to the m is equal to x, and a to the n is equal to y, right? That's the definition. So m is the number I need to raise a to in order to get x. So a to the m should be equal to x. Okay, so then if I think about x times y, this is going to be a to the m times a to the n. So using the exponent rules, it's a to the m plus n, because I add the exponents when I multiply with the same base. So that means log of a of x times y is log base a of a to the m plus n. Okay, and we know that that's m plus n, right? So this one is from rule 3. If I have log base a of a to some power, it's just the power. Okay, but m and n, this was actually log base a of x, and n was log base b of, a of y. So we showed that the log of the product xy is the sum of the logs of the individual x and y. Okay, so that's just a little proof. Notice that I just used the exponent rule, essentially, right? So I turned them into their exponential forms, okay, and then I looked at the product, used the exponent rule to add them, and then I was able to get that out from the log. So another rule that we have, if you have log base a of x to the r, you can actually bring the r down. So this that we want to be careful is the r is on the x, okay, so it's on everything inside the log. So this is actually r times log base a of x. Okay, so you can drop down the log. This last one is a bit weird because there's nothing really to do, but this one is called the change of base formula. Okay, so what I can do, if I don't like base A, I can switch to base B. Okay, now B needs to be an allowable base, so it needs to be positive and not equal to 1. So I can take log base B of x if I divide by log base B of A. Okay, now this you can use to compute stuff. So say I wanted log base, I'm trying to think of something that's nice. Log base 4 of 8, say. So this is not a nice number because 8 is not a power of 4, but I could switch to base 10 or base E and use my calculator, or here I can also switch to base 2. So it's going to be log base 2 of 8 divided by log base 2 of 4. Okay, now log base 2 of 8 is 3, and log base 2 of 4 is 2. So this one is equal to 3 over 2. And it turns out that 4 to the power 3 over 2 is equal to 8. So in fact, 8 wasn't a power of 4, just not an integer power of 4. Okay, so you can use that to use your calculator or to turn it into a nicer base that you know how to work with. So those are the rules. Now, one thing that's going to be really useful is to break apart a log. Okay, so here I have log base 2 of this complicated function. So what I can do is use these rules to rewrite this function as a bunch of addition and subtraction of a bunch of logs. So when I see a fraction in here, I immediately think, okay, I want to use the fraction rule. So it's going to be log base 2 of 2x squared minus log base 2 of the cube root of y to the 4. Okay, now I see that I have multiplication in here. I cannot bring this 2 down to the front, because it's not on the 2 here. Okay, so what I want to do is separate these two first. So I have a 2 times an x squared. So I can rewrite that, oops, I'm in blue. I can rewrite that as log base 2 of 2 plus log base 2 of x squared. Now this one over here, I'm going to rewrite the inside. So instead of cube root of y to the 4, this is actually y to the 4/3. Okay, so now log base 2 of 2. Now because the powers are on the entire thing inside, now I can bring them to the front. Okay, so this is going to be 2 log base 2 of x minus 4/3 log base 2 of y. And then lastly, we know log base 2 of 2, this is 1. Okay, now this seems like we made it more complicated, but when we want to take the derivative, it's actually going to be much easier to take the derivative of this than it is to take the derivative of that. Okay, so it doesn't take very much to break it down. So it's going to be better to try to break it down whenever possible. So let's solve a few equations involving logarithms. So suppose I want to figure out the x values for which log base 4 of x is equal to 5/2. A common thing that we do is switch to the exponential. Okay, so what this says is the base 4 to the power 5/2 is equal to x. I know how to compute 4 to the 5/2. Okay, so this is square root of 4 to the power 5, which means that x is 2 to the power 5, which is 32. Okay, so that wasn't so bad. And 32 is a positive number. Okay, so it can go back in here. Okay, what if x is in the base? Okay, well, let's try again. So let's try and switch to exponential. So this says the base to the power 3 is equal to 8/27. I know how to solve that too. Take the cube root of both sides. So I get x is the cube root of 8/27. And both of these are nice cubes. So this is actually 2/3. And 2/3 is an allowable base because it's positive and not equal to 1. Okay, so that would be a solution. Now here, I can't switch to the exponential form because I have this addition, but I can use the log rules to put it together. So instead of log x plus log of x minus 3, this is the same as log of x times x minus 3 inside. Okay, now once I do that, now I can switch to exponential form. Now remember, when they use log with no base, they're assuming base 10. Okay, so if I go to exponential, that means 10 to the 1 is equal to x times x minus 3. So if I expand, this is x squared minus 3x. I'm going to move the 10 over. Okay, so I want to factor this, and it factors as x minus 5 times x plus 2. So I get x equals 5 and x equals negative 2. Now, I want to be careful, so we should check that these work. Okay, so if I check x equals 5, and I plug that in, okay, that's log base 10 of 5 plus log base 10 of 5 minus 3, okay, equals 1. So this says log base 10 of 5 plus log base 10 of 2 equals 1. And because I have the addition, this is actually log base 10 of 5 times 2, okay, which is actually log base 10 of 10, okay, and that is equal to 1. Okay, so this is a solution. Okay, I'm going to switch colors here. Now what about x equals negative 2? So I would have log base 10 of negative 2, so of x, plus log base 10 of negative 2 minus 3. And I'd want that to equal 1. Okay, well these, I don't have a lot of room here, but both of these are undefined. So you can't take a log of a negative number. So because it's written the way it's written, this is not a solution. Okay, so this one we say is an extraneous solution. Okay, so it's not actually a solution. So the reason why it kind of works is because when I put these together, I end up with negative 2 times negative 5. So I end up with a positive number. But because it's written like this with the plus, I need it to be defined at both of these logs. So because they're not defined, I throw away that solution. So the only solution is x equals 5. So you want to be careful because of the special conditions on the base and also on the domain of the logs. It's very important when you're solving log equations that you check your answers. For extraneous ones. Okay, so you want to check that. So even in the first two, I made sure to think about, can I plug that back in? Yeah, and we could for both of them. Okay, so that's a brief introduction into logarithms.